Fluid mechanics is a branch of physics that studies the behavior of fluid flows. From an engineering perspective, when solid bodies such as a car, an aircraft, or the flat plate that we see in the movie move through air, the interaction between the fluid and the surface conditions its maneuverability and the drag force which opposes its motion. The growth of computational power in the last decades has made it possible to simulate the behavior of fluid flows around moving objects, featuring realistic surface roughness. In the movie that is currently playing, we observe the instantaneous evolution of vortical structures behind an isolated roughness element. In the simulation, we numerically solve the Navier-Stokes equations, which are the set of equations that rule the behavior of fluid flows. These equations capture the two main states of a fluid, the laminar state and the chaotic turbulent one. In our research group, we study the process by which laminar airflow transitions towards a turbulent state on the wings of subsonic aircraft. Wings are not smooth, but rather contain surface imperfections. Misalignment between wing panels in the manufacturing process introduces roughness in the form of spanwise-distributed steps, which promote laminar-turbulent transition and render large areas of turbulent flow. As a consequence, the skin friction rock increases, which carries an important economical and environmental impact. We perform direct numerical simulations of the effect of steps near the leading edge in a representative area as the one indicated by a block rectangle. We investigate the interaction between a dominant boundary layer instability in swell-wing flows, the stationary crossflow instability, and forward-facing steps. To study the problem, the wing is modeled as a flat plate with an imposed airfoil-like pressure gradient. The three-dimensional boundary layer is resolved, as well as the perturbation field, which is Fourier transformed. From our simulations, we find that the incoming fundamental crossflow instability lifts up and passes over the step. Near-wall perturbation streaks are induced, which coexist with the primary structure, but rapidly disappear further downstream. The existence of secondary perturbation structures induced by the step is further demonstrated by analyzing the topology of the projected perturbation streamlines. In the no-step case, only primary structures exist, whereas in the step case, additional secondary vortices are induced upstream of the step. Downstream of the step, secondary vortices grow and become much stronger than the primary ones, and eventually merge with the pre-existing structures. The impact of the step on the wave-like perturbations is assessed by tracking their amplitude. When compared to the no-step case, small and medium steps are observed to amplify the crossflow mode. When considering the largest step case, which reaches up to 50% of the boundary layer thickness, amplification is captured upstream of the step as well, but a strong modulation is observed in the downstream region. In the following stages of our research, we will connect the mode distortion introduced by the step to the growth of unsteady disturbances and corresponding turbulent breakdown.